Thank you for attending my talk and thank you for hosting a wonderful workshop. It's a great pleasure to share what I've been working on in the past few years with all of you. I'm excited to attend everyone else's talk and have more discussions throughout the 3 days. This is very mysterious title. I'm not explaining what the title means. Of course, it's a joint work based on the joint work with many of my students, my postdocs, and my collaborators and their students. Let's jump into the title, what the title means. I guess everyone knows that most of the current large language models are based on the single design principle. I summarize it in decoder-only next-door prediction. What does that mean? And if I have to decompose it into two parts, there are two things that are common across all the language models out there that are successful. One, when you generate the answer or the output, there are multiple tokens in the answer. And the fundamental inference mechanism that everyone's using is iterative next token prediction one by one from left to right. Basically, it's autoregressive generation. The other one is architecture. Everyone is basically relying on some variant of decoder-only transformer with their own variant. Let's just explain what that is. So when you're given a prompt, let's say the prompt is 123 plus 789 question mark. Then what the model does is first predicts one token 9, feed it back by concatenating the input prompt with the one generated token and generate the next token. And you keep repeating this again, and that's how most large language models work. By decoder-only transformers, what we mean is when you have one new token generated, that token will not affect any of the embeddings computed in the previous token by definition. Well, of course, is this the only mechanism for inference and architecture? No, there are many other choices that people are working on, various different approaches. This talk is going to touch upon some theoretical understanding of what the other algorithms and what the other architectures can do instead of decoder-only next-door prediction. So the first part will be about inference mechanisms. Second part will be about architecture. I'll probably talk about the first one for about 20 minutes. The other one about 10 to 15 minutes. So I was actually teaching a course on large language model last year. I was reading this textbook, and they actually say like for large language models or language modeling, it is very natural to do autoregressive generation from that right. There's a single sentence saying that there's stronger predictive modeling. It's much easier to learn how to predict the next token from the previous tokens because the data is causally structured. There are of course, most of the natural text data is easier to predict from left to right, but there are also cases where that's not the case. This is not natural text example, but I'm just giving you a counter example, which is more like carefully designed for this example. But let's say I'm adding numbers using transformer. Why do we have to add numbers with transformer? Of course, you don't have to, but let's say just consider this as an example. So the output has 3 tokens. If I use single digit by digit tokenization, then if you want to predict the answer 912 from the beginning, left to right, it's a very complex function because to predict what the first digit is, you have to actually see all the tokens in the prompt. You have to compute all the possible carryovers and so forth, and only after that you can compute what the first digit will be. On the other hand, if you predict the third token first and try to predict it backward, predicting 2 is super easy because you have to look at 2 numbers, and you just have to do something called calculation, addition, or 10. You can see that you can basically, in other words, you can decompose the output generation in whatever order you want. Certain orders will be much easier to learn, certain orders will be much more difficult to learn. In this example, reverse order is much easier to predict. And in fact, this is one experiment we ran when we were working on this paper with Dimitri and our students, Nayeon, Kartik, and Jason. This is number of examples we use for training transformer from scratch. We have a data set consisting of this kind of format. So literally we have digit by digit tokenization, bunch of numbers added together and the answer. So we try to train transformer from scratch to see which order is easier to learn. And if you look at the red curve, that's the accuracy of the forward trained transformer. The reverse trained transformer is going to achieve 100% accuracy much faster. forth. So it's clearly showing that not only just the intuitive way of seeing that it's easier to learn, it also utility show that reverse is not easier to learn. In general, not only different orders of autoregressive way of generating tokens, there could be completely different ways of generating. And non-autoregressive generation can be viewed as you generate something, multiple tokens, and you can also go back and revise, and you can do whatever you want. So anything that's not autoregressive generation can be viewed as non-autoregressive generation. And in fact, if you think about diffusion models, some of you might be familiar with what diffusion models do for generating images or videos or audios. They basically start with a fixed dimension vector and iteratively refine the vector over and over until it becomes something that you wanted to generate. And similar idea has been also explored for language modeling as well. In fact, I don't know, maybe I'm missing something, but if I go up the history, it's like 7 or 8 years ago, people were looking into the same ideas. Recently, they found a similarity between what they've been doing with diffusion models. We started calling it diffusion language model, and people are working on this. So basically, the idea is you start with a random sequence of tokens like this, and you try at test time, at generation time, you are trying to go back one by iteratively denoting the sequence of tokens until you get defined a sentence. During training, you start with the clean sentence, try to corrupt token by token at random, and you get the sequence of forward generation. Well, this idea has been around for quite a time, but hasn't been successfully scaled to the point like multi-billion models parameters. Very recently, like these are all this year's paper. This is from I think February or January of this year. It started making it scale up to 8 billion and showing that the diffusion model-based language model with 8 billion parameters successfully achieved higher accuracies than GPT with the decoder model, the transformer-based network computation model, which is Llama. And also very recently, you probably have seen this video from the company called Mercury, the Inception Labs, and this is the model called Mercury. And they are showing that another advantage of doing non-autoregressive generation is they start with huge amount of tokens at once, and they iterate it, but the number of iterations that you need to do is much smaller than the number of tokens, so the actual generation time could be much faster than token by token generation. So in the first part, what I want to talk about is what can we talk about this non-autoregressive generations in theory? Well, of course, I guess many of you, I'm trying to list up some of the papers I recall. Sorry if I'm missing anything important. AR generation, token by token generation, possibly with COT or some filler tokens or pulse tokens, particularly focused on transformer. That's been the focus of the study in the theory work. And also we know what the COT does, what we know attention is doing, what DAPS is, when the DAPS is useful, what parallelism of attention is doing. We have better and better understanding over the years. But the non-AR generation, particularly with transformer, has not been studied much. So I'm going to introduce some of my past work that actually touches a little bit of what non-AR generation can do with transformers and what transformer can do when it comes to non-AR generation with this 2 papers. The first one is about, I'm going to show that non-AR generation, particularly adaptive, I'll explain what that means, can actually execute any program. So it's very powerful. So we're given any program, you can view that as a generation process, and you can show that transformer can generate, simulate any program experiences. The other paper is a very recent one. We can show that non-AR generation actually can learn how to solve algorithmic tasks in a more or less generalizable way. I guess we'll hear more about less generalization later today, but the brief touch upon what less generalization is. Well, any questions so far, by the way? I'm happy to make it more interactive. Feel free to interrupt.
So questions, so maybe we'll discuss this later, but so for the diffusion generations, do you have to fix the generation length before during that generation?
Yeah, great question. So in most cases, yes. You have to deal with the predictive length of the output is something that some of the work is trying to have 2 separate problems. One, given the prompt, you have to first predict the output length, and then use the iterative generation with the fixed predictive length. But yeah, I'm not so sure about whether you can have it more like flexible length while generation. I haven't seen that one. In most cases, yes. what do I mean by program execution? Well, if you think about how we actually run a program with the computer, and if you see the stream of the memory state over the time of running a program, you can actually view it as a generation. Because what I want to generate is the output of the program, which is somewhere in the memory in the end. In the beginning, the prompt is my program code and my program input, and that will be staying in my memory. And if you see the process of running a program, the state of the memory can be viewed as a basically history of non-linear generation. At the beginning, you have some prompt. At the end, you have final output one responder. Taking a program and simulating the process of the computer program execution is actually a very good model for simulating or maybe understanding the non-linear generation. So for that purpose, we consider this single operation computer, which is sublec. It's short for subtract and branch if less than or equal to. I don't know how many of you have heard about this one, but this is a very interesting instruction. It has only one instruction with 3 arguments, A, B, C. So given A, B, C, what it does is first reads up the memory values in B and A, subtract memory A from memory B, and update memory B. So there's some reading operation, subtract operation, writing operation happening over there. And then you either go to the next instruction, or you go to jump to instruction C, which was the 3rd argument, only if the output of the subtraction becomes negative or non-negative. So it has very simple operation subtraction combined with the branching thing, and then it becomes string complete. And the key theorem that we showed in this work is you can actually implement one round of this instruction execution with a finite depth transformer, which is particularly 9 layers, 2 has with the width of the transformer scaling with the width and also the size of the program or size of the memory. And what that also implies is now, given this theorem, what you can do is you can have a 9-layer transformer with an external out feedback loop that takes the output of transformer, feed it back, and it becomes a computer. And then if you look at the evolution of the output tokens, sequence of output tokens during this execution of the program, it actually becomes almost like non-linear generation.
What is bit width?
Oh, bit width is, so when we are reading the data from the memory, somehow we have to start define how many bits are going to be assigned for each memory slot. That's what I mean by bit width. Basically, precision of the data stored in the memory.
So is there something sort of fundamental about this particular operation?
No. Good question. So why did we choose this operation? Well, we wanted to show that you can implement transformers such that within a loop, they can run any program, not string complete. But then we just wanted to choose a simpler case where we have only one instruction to implement using transformer, but you can choose any other instruction that you want.
Do you have any sense whether the number 9 is close to type? I ask because it feels a bit inefficient in that this seems like a natural thing. Something like this could be something that a real transformer would want to do. But then, these like GPT models, I think they're like 100 layers deep. So using 9 layers to just do this seems a bit inefficient.
Yeah, I don't think it is efficient. It is. I'll show you the way we constructed this. Very inefficient in that sense. You could totally optimize it further. I don't know whether the fundamental bound will be. I don't think you can do the whole instruction with 1 or 2 layers, but maybe you can make it down to much smaller than 9. Okay. So the construction is pretty simple. I'll just show you a very high level construction sketch. As I mentioned, if you look into this instruction, you have to implement how to read the command, which is reading ABC from the current program counter. And you also have to read up the data from the memory B and memory A. You have to read it and bring it to your, let's say, cache memory or scratch pad. We'll talk about it soon. And you have to do computation, which is subtraction. And then you have to write the output of the computation to the memory, the right memory place, and you have to do the branching. So these are the 5 operations you have to implement. And to do that, what we are doing is, you can think about this as the sequence of tokens. So every column is a token. And we divided the input sequence of tokens into 3 sections. The last section is the where the program exists. And we are reserving the first multiple rows to reserve for writing down the program, and we do not touch that. That's the program code that comes as an input and never changes over time. And so while the program is running, it jumps back and forth depending on the branch factors to run the program. The second column and the second row block, this block is for the memory where the input program input is coming. So these are the the height of this one is basically the bit width of the data. And then this part is the scratch pad where you're actually implementing the calculations, storing the intermediate values required to run these things. Basically, it's internal memory of the CPU. And what we do is, using this particular embedding structure, we are implementing this functionalities one by one. It requires a few layers here, a few layers, 1, 2 layers over here, and then add it up to 9 layers. That's how we construct it. And that's the end of the proof. It's a construction. It's an existence proof where we show that the transformer can mimic the entire behavior of this single instruction program computer. And then once you do that, you can actually program whatever you want using the particular instruction set. And then you can see that transformer is running your program for yourself.
And do you need a larger number of layers to do? I mean, how does the number of layers scale with the complexity of the program, or does it not?
The number of layers is fixed as 9 here.
Okay.
Because 9 layers is you're doing the exact same thing for every clock of the CPU basically. But the runtime depends on the length of the program, not the length of the actual runtime of the program. If the program has a lot of for loop, it will run for a while. So the number of iterations, that's going back to what I mean by adaptive, because this program, the loop will not end until it hits the end of the program. So the actual runtime or how many times it will iterate over and over depends on when the program ends, and we cannot determine before we run it. Great question. There's also a little bit hinting some slightly different thing between what we are doing with autoregressive generation, diffusion language modeling we are doing, because there we do not usually change the number of steps. But here, at least from the construction, when we are trying to mimic the program execution, the number of iterations is actually not decided before we run it, because it depends on how the, so we are basically seeing that it's like running the program and see where the program should end. In some sense, the number of loops is determined by the model itself and the data itself. The second example we want to talk about is the algorithmic task. We wanted to train transformer to do some algorithmic task, let's say addition or multiplications, some kind of algorithmic functions. And one critical aspect that people are looking into this in this context is length generalization. We'll hear more about it later. But the idea is that you train a language model up to particular difficulty. And at test time, you try more difficult problems and see whether the model actually learned the algorithm, whether the model actually just memorized how to solve some easy problems in the training set. And in fact, what we know is the decoder-only next prediction does not actually length generalize at all. So this is an example where we are training a transformer on addition, as I showed you before. We are training transformer on 19 bits, two 19-bit sequences, so A1 to A19 plus B1 to B19, followed by 20-bit answer. And at test time, we are testing with 20-bit input digit, 20, 20, 20, 20, 21, 22. So you're testing it with more number of bits. You can see that the accuracy stays higher for a few more bits, but later it just goes down like that. So that's a known phenomenon that the transformer seems to be working very well on from digit 1 to digit 19, but at test time, if you test 21, 23, 25, it starts going down. So what is the problem with this? How do we solve this? We'll hear more about this conjecture later, I guess. But So I don't want to talk too much about it. But this is a really nice paper. We actually got inspired when we were working on our problem. But basically, in short, if there's a single Cosel transformer weight you can construct without using some sophisticated operation, that's by what we mean by simple here. If you can construct a single transformer that can actually solve the given algorithmic task at arbitrarily different input lengths, then we conjecture that this will, once we train the model, it will length generalize. That's the Vasil generalizing conjecture. Hopefully I did it right.
That's great, thank you.
We'll hear more about the from the expert later today. But then depending on this, these are the cases where we know how to construct a transformer weight to solve this task of counting, computing the mode, sorting. We know how to find the transformer weight that does exactly solve this problem for any length, while these are the problems where we don't know how to construct the answer. I don't think there's any impossibility research yet, but for instance, addition, we don't know how to construct a transformer that can solve arbitrary length addition without using some complex operations. So without being not simple. So this is the kind of extension of our version of the previous conjecture. What we are doing is, well, let's consider the autoregressive generation, non-autoregressive generation. Instead of just generating one answer and one token by token, let's generate the full answer and try to revise again and again. So it's a completely different way of generating the answer. So now, but then we need to also have the transformer in the loop. So what we are doing is using a causal transformer. We still use the causal transformer, generate the whole output, but in a loop, so you can revise again and again, very similar to what we did in the past. And what we can do, what the new conjecture we have is, if you can construct a single transformer, such that if the single transformer in a loop with adaptive number iterations, such that it can solve the exact algorithmic task we can do, then we think it will then generalize. So let me, and then following, given this conjecture, what we can show is, in fact, we can construct single transformer weight that can solve addition, copy, and parity. These are the three tasks that we couldn't solve with a single transformer without loop and predicting next token one by one. So now we can solve this task using this loop and also non-autoregressive generation. And then explain what that does. It's kind of weird thing, but we'll explain one by one. So think about this. So now I'm given this prompt, and I have this. Usually, when you're doing next token prediction, you're trying to predict one token over here. But what we are doing is we are predicting the whole output. So given this, we're going to predict like the same length output in the next iteration, and we'll revise them over and over. And here, because there's no input given, I'm going to put some like random question mark or the empty token over here. So the first iteration does this. So you have to make sure that everything I'm doing is causal and not crazy. So this is causal operation. This is just pre-processing. What I'm doing is just moving things like this in particular order. So first, there's nothing crazy. So. But then the next one is addition. I'm doing the addition of these two consecutive numbers and put the addition over here, mode 10. And here, if the carry is written over here. The two number addition added, and if it's larger than 10 or equal to 10, that's 1. So then I do repeat the same thing. So 4, 5 becomes 0, 9 here. 5, 5 becomes 1, 0. So far, it's a very simple operation because I'm just looking up two nearby numbers, computing an addition or larger than or equal to 10. Then I'm shifting. So shifting on the numbers in the gray columns remain the same. Numbers in the white columns shift by 2. Now you do repeat the same thing again. So if you look at this, every operation is causal, every operation is super simple. But at the end, and then you can see that the addition shifting is repeating again and again. And at the end, you get the final answer, which is 1000, which is exactly the same answer, the correct answer is the answer. So what that actually means is that that's the proof of the proposition I mentioned. So there's a single transformer that can implement this repeating operation, addition and shifting, up to pre-processing and post-processing. So that satisfies the conjecture. And we believe that if you have a loop transformer, you should be able to learn how to add numbers in a length generalizable way. So that's our conjecture. And this is the example. Let's give this one. And we actually ran experiments. So this is like the exact architecture. We take the GPT-2 size transformer, about 100 parameters, and we put in a loop. Okay. And the way we train this one is you have the input problem like given, and there we have like bunch of like empty tokens over here, and you loop this transformer many times, and at the end of the multiple iterations, we give the loss over the multiple output tokens at once. We are not doing any next prediction here. So it's very different from what people usually do, because we do the multiple iterations, and we only measure the loss at the end of the generation. And these are more particular details. How about how to make some residual link between this one and the within the loop. I skip those details. In fact, these are very related to the paper called Universal Transformer that actually does something very similar to one what we are doing here. In terms of architecture, we borrowed many ideas from this paper, more like a simpler version of what the Universal Transformer was doing. And the result?
So over here, do you learn a separate function that tells you when to stop looping? So when do
That's a great question. So the short answer is no, we are not learning how to stop here. That's kind of our first version here is during training, we are using the exact number of iterations that we constructed. So in the construction, we know the exact number of iterations that is needed. So for instance, addition of D digit, we need to we know that our construction requires D iterations. So during construction, we give the exact ground truth number of iterations during training. And at test time, what we do is there are two things. You can also use the ground truth answer. You can view that as kind of side information. Let's say you're given like D+1 test, but then you need to run D+1. If that is the case, that's the easier case, we use the ground truth number iteration. That's working much better. The other case is we actually use the output confidence to stop. Another learned algorithm. So it's and like sometimes it's not working, sometimes it's working. Out of the 6 tasks, we found on 5 tasks, just looking at the confidence actually works pretty well. So if you look at the confidence of the output of this, all the tokens that you generate, you somehow take the average of them, you look at come up with some single metric. In fact, even for unseen length of the problem, unseen difficulty of the problem, the confidence actually works pretty well. But yes, making it how to learn when to stop. In fact, the universal transformer actually has 2 components at the same time. Iterate while over and over, and also they learn when to stop. That's why it's also more, I would say, more expressive, but we just chose this one for simplification. As a result, what we see is, well, the loop transformer is really good at generalization. Does not decay over up to 10 more digits. And you can see more bigger in the bigger and for some simple task, it actually generalizes over 50 digits over the training digits. So we found that the non-linear generation with loop transformer is actually pretty good at solving algorithm task reform. And these are some other tasks there. So these are the first 3 tasks we showed there exists a transformer in the loop that can solve the problem. The other 3 are something that we haven't proved, but still in practice it works pretty well. Question.
Quick question. So what would happen if you did a loop transformer, but still did autoregressive generation, didn't have the non-AR part, but allowed this looping? Would that be enough, or is it necessary to have this non-AR component as well?
So I think this is the NTP loop. Is exactly what you suggested. So we are not doing we are still having loop transformer, shared weight, multiple iterations, but we are still doing the next competition, non-autoregressive. It is most cases. You can see that it's actually much better than vanilla next prediction. But in most cases we are, and this is also pretty much close. So yes, there's some gain just by doing a loop, but I think the non-autoregressive generation is also pretty much a big deal. I'll tell you more about it offline because it's sort of differences between them. But also there are some things similar between them. Great question. Great question. I'm pretty sure my student carefully chose the end of the graph just before it goes really fast. Just kidding, but I think I'm pretty sure parity we tested up to like something like 60. It was pretty fine. I think it goes all the way to 100-ish. Addition, I think goes down something around 40 to 50. So yes, you will, if you increase the access range by a factor of 2, I think you will see some degradation. Good question.
So, but provably there is a, for addition, there is a configuration of the transformer that was just indefinitely though.
Yes,
Right? So then this tells us that the training did not find the exact correct algorithm.
Exactly, yeah. That's the same for the rather cases as well. Even for simpler tasks where you have a single transformer that actually, without any loop, they can solve the task. The Rust conjecture says that we can find the transformer that can solve the problem in a more less generalizable way. But in fact, it's not exactly the same architecture, so it also fails over to testing the really large problem. Yeah.
Would you need more intermediate steps to do that model?
Oh yeah. So in fact, I think this is the kind of oracle case where we know we are scaling the number of iterations proportional to the size of the input. But yes, in general, we assume that that is known. But without knowing the difficulty and how many iterations we need to run, we also have separate figures which has little lower performance. So now let's wrap up the first part. So I think these are not, in fact, none of this work were particularly designed work. We didn't have any mind that this is for understanding non-AR generations of language models. But I'm just giving you a kind of different perspective of how we can interpret these papers, because now I think it's time to revisit all these assumptions that we had in large language model. We were running so fast without looking back, and to revisit the kind of assumptions that we have made in the past. What about non-AR generation? I'm learning a lot from like reading old papers, because apparently NLP people have looked at so many different ways of doing non-AR generations. But anyway, so this is from our perspective. I think the key takeaway from our work I found is I think we need to really have some adaptive number of iterations that goes into the diffusion language model as well. And also, if you look at the way we are constructing our algorithms, there's no diffusion happening. The only thing that we are sharing with our approaches, our constructions, and diffusion language models is there's some like iterative revision of the full output over and over, but none of the forward backward is diffusion. So in some sense, somehow we probably want to learn both backward and forward processes if we really want to make it powerful. And so in some sense, like we were doing some kind of similar approaches for fine-tuning diffusion models. We're doing this. That's one part of the approach. The other thing that's more interesting theoretically is there any fundamental trade-off between doing AR generation versus non-AR generation? And in fact, non-AR generation from our constructions, they use smaller number of iterations, but they are doing entire parallel decoding over and over. And AR with COT, I think there's no expressive power difference between non-AR versus AR, but you need to like do token by token, which is like many more sequential decoding. So, but then like in practice, in the memory bound regime, this time that goes into one parallel decoding and one sequential decoding is pretty much the same. So that's why I think people are also excited about non-AR models become much faster in practice, because you generate like 1,000 tokens at once and iterate over 10 times. That takes about time to generate 10 tokens. So there could be some fundamental trade-off. It kind of reminds me of the protein network, and you can see that like make use of the parallel computing and see whether there's any trade-off between them. With that, we'll move on to the second part. Any questions on the first part? So the second part will be much easier. I think I have about 5 to 10 different minutes. Decoder-Only next token prediction, the assumption is the new token cannot affect the previous token embedding. Well, why do we need it? In fact, you don't actually need that. So let's just get rid of the assumption. That's basically what we mean by encoder-only next token prediction. Let me see if there's any question. Okay, anything wrong here or no? There's nothing wrong with. I'm trying to break the assumption that why do we use decoder transformers for next token prediction? Do we have to? Let's go back to the script. Let's spend one more minute on here. Why do we use decoder-only next models here? Because why do we have to prevent the new token input from making updates to previous tokens embedded?
efficiency?
Yes, the answer is efficiency. Like if you don't care about efficiency, there's absolutely no reason to do this. We'll talk about, so basically NCBS, let's forget about efficiency. There's no reason to use decoder-only prediction. So let's just see what happens if you just get rid of that and see there's a little bit of improvement in terms of expressiveness of the model. So let's go back to the efficiency part. So the causality or the causal masking is purely for efficiency because the new token cannot affect the previous token's embedding. Therefore, you don't have to recompute any of the embeddings from the previous token when you're generating more tokens again and again. But if you completely ignore the efficiency, then there's no reason to stick with that assumption because given x1, you generate x2. Now you just recompute everything with x1, x2. X2 can potentially affect the embeddings of everything coming from x1, and you can do it again and again. The pros and cons are very simple. Pros, this is a much more flexible computing model. You have more compute, more memory per token, so potentially more expressive. Cons is you have to recompute the embeddings from scratch every time you see a new token. So computing time is not anymore n squared, because here you're sharing the computation, so you can have n squared. But here you're recomputing everything, so it's I squared. It's the sum of the I squared, so it becomes n squared. So it's both for training time, testing time. To train a model with n number of tokens, you spend order n cubed, and also generation time takes order n cubed. So it's going the other way around. Like I know, like linear attention models like Mamba, those things are for like making it more sublinear, more subquadratic, closer to linear. But this is like going to cubic, trying to make it slower and less efficient. Let's see what we can do. So first, quick statement. You can actually compare the kind of function classes defined by encoder model and decoder models. And turns out that a little different from my previous expectation, but in fact, they do not overlap. They do not subsume each other. So the class of sequence-to-sequence function represented by encoder models and decoder models, they overlap. But decoder-only model also has their own unique area. So it's interesting because it turns out that decoder-only models also has its own causality that can be used to represent some function in the decoder.
Could you say a bit about like what type of separating are here?
What types of?
Yeah, like what are the separating?
We'll go to that. Yes. Yeah. So we'll talk about the function class that example of this function in here. We'll talk about the other one often. So this is the example. It's we call count3. Initially, we didn't know the similar example was done by Daniel's paper. So later they told us about this paper and like the similar example they had. So we renamed it because it's too similar to what they had, which was match3. So it's count3. So what count3 is doing is you're given n tokens as an input. The output is you count how many triplets you have within this n tokens that sum up to 0, up to more than. And so to give you an example, like you have 16 numbers over here. The 17th number should be you count all possible triplets over here that sum up to 0 up to both 16. That gives you a new number. You can keep generating numbers that determine easily like this. And you can see that this is carefully designed to break the limitation of transformer because they are inherently n squared. If you're doing the decoder-only transformer here, the computation is bounded by n squared. This one actually requires n cubed to compute, so that's why it's designed this way. With some assumptions, there's some hardness conjecture we have to assume to prove the impossibility result for decoder. But for encoder, we can show that encoder can solve this problem with constant number of layers. But for decoder, with some hardness conjecture we have, you can show that there's no decoder that can satisfy this problem, solve this problem, unless you have some pretty uniform layer. There's one slide that actually shows the relationship between the work from Daniel's group and this work, but let's skip this one more because we'll talk about offline. But this is super interesting empirical result. What we do is we can actually take the transformer from scratch or take the transformer pre-trained models, either bidirectional models or one-directional model, they can see whether they can actually memorize and train on this sequences and see whether they can generate the sequences at test time. And turns out that as decoder models, no matter how big the decoder model is, they always get 0 here. And the NTIP or encoder transformer, encoder next prediction or BERT, they can achieve almost 100% accuracy. You can run the same experiment for even larger decoder-only transformer models. This is pretty cool because we use the GPT-4 API to fine-tune GPT-4o with like many sequences generated from the model. At test time, you give a new model, a new test sequence, then it completely fails. And it's basically like impossible to solve this problem, assuming our computer is correct. Few open problems. I think our theoretical guarantees are still kind of limited. We didn't identify many useful tasks that live in the E-D part. In practice, we tested something we found relevant, addition in context learning, small language modeling. We also found that encoder-only transformer actually less general is much better than decoder-only transformer. So that's also something we found interesting. There's no theoretical guarantees, so working on those things is important. The other thing that I'm particularly more interested in is less theoretical, but is about making NTIP idea more practical. Because right now it's like we're completely giving up the practical efficiency, but I think there should be some compromise architecture that somehow keeps the advantage of the efficiency of decoder transformers while making it a little more expressive. One example would be adaptive KV recomputing. So basically the reason why this kind of problems cannot be solved by decoder transformer was that you have fixed KV compute over the past tokens, you never update them. So you have very limited computation per new token. But if you enable this kind of recomputing of some KV caches whenever needed, then it could actually expand the expressive power of my alert. I don't know how to do it well. I'm thinking about it along this direction, but happy to discuss more. With that, this is what the title was. Talked about the architecture-wise. I think most people are working on decoder-only, but encoder-only has a completely new avenue. Theoretically, you can show that it's better. It's not practical, so somewhere hybrid might be an interesting thing to discuss more. Next token prediction, most people are working on autoregressive generation from left to right, but non-AER generation is becoming more and more popular. We still have less theoretical understanding of how they work. There are lots of interesting problems. Doesn't necessarily have to be diffusion models. Could be some non-diffusion, non-AER generation as well. So with that, this is based on the work with my collaborator students down there, and thank you for listening.
We have time for a couple of questions. So,
So I guess in these algorithmic tasks, like the power of like the non-AR model is very apparent. But in some sort of like perplexity experiments that I've seen, like people have argued that left to right models, you know, attain much lower complexity than say like left models or even diffusion models where they're like variation lower bound. So I'm kind of curious whether you think this is like architecture that's specifically useful for algorithmic settings, or do you also think it would eventually be useful for like general language modeling kind of?
Yeah, great question. So, the question was about particularly about non-AER. I haven't actually like tested any of the non-AER ideas on beyond algorithm tasks. I have no good idea about that. In terms of this one, we have compared the decoder-only transformers trained from scratch, encoder-only transformer trained from scratch. The problem with NQ, we didn't go all the way to the big scales. But at least for small scale, we found encoder transformers always get lower problem. So if you're willing to spend like millions of GPUs, then you can train encoder transformers with better complexity. But I don't have good answer for that.
So I probably understand encoding decoder exactly, but in my head, I thought the encoder architecture would always do decoder, right? Do causal stuff. Like, what is the intuition that you have a problem that can be done by decoder only, but not encoder only?
So can we go back to this one? So you said that encoder can always do decoder things, or I didn't get that part.
Yeah, so my understanding is that it's, you know, the second thing, X1 and X2 depending on each other, X2 is different than X1. It seems like you should be able to simulate what you're doing
with, so this is what encoder-only transformer for network operation. So whenever a new token comes in, you recompute everything.
Right.
So you have more memory and you have more computation.
Yeah, but should be able to simulate everything on the left, right? Because
Ah.
it will be possible.
But here, because of the causality, so when the new token comes in, this is basically fixed memory.
No, I understand.
Mhm.
In my head, the thing on the right can always be similar to the thing on the left.
Similarly on the left, with causal masking or no? With causal masking, no, because you cannot update this one. So in some sense, if you're particularly looking at what the compute and memory given when generating X4 with X3, this is kind of memory that is fixed for you.
Right, but given the stuff on the left,
Mhm.
there is always an instantiation on the right that can simulate the thing on the left, right? Because on the right, you're allowed to look back, you're not.
It's not just looking back, you're updating as well. This is bi-directional encoder.
Yeah.
So you're also updating the content.
So the thing on the right is more powerful than the thing on the left.
Yes.
So then how do you get a problem that thing on the left can do the thing on the right cannot? You have that Venn diagram.
Yes.
Yeah,
So.
you have something in TD which is not in TE, and so my.
Oh, okay. That's a question also we had before. This is the tricky part because, so that's my initial expectation was this is strictly bigger than this one. But apparently there's some inherent causal pattern that is embedded in this architecture. Makes it, this model easier to learn some particular types of sequence function, very specific function. Let's say, I'll give you one example. Let's say, if your sequence function is actually like, very good, very aligned with this kind of causal pattern like this one, where you shouldn't look at, I'll give you the exact example where this can only implement, but this cannot. But yes, there are cases.
Starting resource problem.
No, it's just like the actual fundamental.
Okay.
We'll talk about more.
Yeah.
Okay, so we should, let's just thank Kangwook Lee.